Okay, so another video introducing another circuit component. Today we're going to talk about inductors. Now, inductors are an application of magnetism on circuits. That's okay, we don't actually have to go much into magnetism on this, but to understand the underlying principles of how an inductor does what it does, you'll actually end up with Lenz's law and kind of forces, magnetic forces coming from currents. In short, we have things, the way I like to describe inductors are, they are the people of circuits. What do I mean by that? They're afraid of change. Most people are. Most people would rather not have things change if they're used to how things are done. Inductors, that's the name of the game for them. They don't like changes in the circuit. Not to anthropomorphize them, but that's a good way to keep track of what they do. In short, what inductors do is try to keep the current the same. But like people as well, change is inevitable. In other words, they're going to try and keep the current the same, but they're not going to succeed in keeping it the same. It will change over time, and it'll change based on some of the things that we're going to take a look at. Now, just like with capacitors, this is going to be introducing kind of the what happens at the very beginning and what happens at the very end, and using some of the equations that go along with that. We'll have another video that goes along with this that actually gives you an idea of the calculus and what happens in between time equals 0 and time equals an incredibly long time afterwards. All right, inductors. What do they look like? Well, they are squiggly. This is in reference to the fact that at least their moderate construction is usually one looped coil around other components. Basically, you wrap the wire in around itself. And that allows for interesting effects that happen with the magnetic field and how that magnetic field will end up having a force on the current, the moving charges that are trying to move through the inductor. This is how we actually end up with induction, with what the inductor actually does. One other thing that I want to bring up before we draw this in a circuit. I mentioned that capacitors store energy in electric fields. Inductors do something similar. Inductors store energy in magnetic fields. So they both kind of do the same thing in a circuit, at least what they're doing energy-wise. They both store energy. We're going to find that in a circuit, they kind of do the exact opposite. Capacitors, at the very beginning, if they're discharged, they will have almost no resistance in the circuit whatsoever. And then as time builds up, so in short, if they're discharged, our effective resistance of the capacitor at time equals 0 is 0 ohms. Technically, we would call this an impedance, but you could imagine it as a resistance that's changing. R of time equals infinity is actually going to be infinite ohms for a capacitor. We're going to find that the inductor is nearly the opposite. At time equals 0, the effective resistance of the inductor, again, it would be best described as something called an impedance, but we don't talk about that as much at this level. You can imagine it as a resistance. It's going to start off with nearly an infinite resistance. And as time goes to infinity, the resistance of the inductor will actually go to 0. So while they do the same thing energy-wise, one with electric fields and one with magnetic fields, the reason why we use them so much in circuits is because they actually do the opposite of each other. A capacitor will let things change really, really quickly and then slow them down and finally bring everything to a stop. It basically is a big startup and then everything slows down and then stops. For an inductor, when you start it, it won't really let you start, but you'll very slowly start moving and start getting things moving faster and faster, and eventually the inductor will stop acting like it is there. However, it will have stored energy in it in the magnetic field. All right, here's how we actually use them. So let's take a look at a simple circuit with an inductor. Here's a resistor, and here is an inductor. Let's throw some random numbers at this. Once again, let's go with a nice 10 ohm resistor. And we're going to have a laughably large number. It turns out inductors have something called an inductance. It acts a lot like the capacitance. It's a number that we use to actually rate the value of the inductor. And it describes, among other things, the amount of energy that can be stored in the magnetic field, among other things. But in short, we rate them with a number called an inductance, and it is measured in henries. Henry, I can't remember if it's an I or a Y. I think it's on the equation sheet. Let's find out. Capital H is a Henry with a Y. Yay! Look at me. All right. Henry, capital H. Now, many times you'll see a more realistic value, millihenry. All of the metric prefixes still apply. Let's say that this is, let's throw something random at it, 5 henries. All right. And, like usual, let's say that we've got a switch. Here's what's going to happen. Oh, one final thing. Let's say that we have let's go with what we did before, 6-volt battery. We'll use a lantern battery. Okay. So, what I'd like to know is this. At first, what's happening with our circuit? In fact, what's the initial current right at, so time equals 0, I close this switch. So at time equals 0 seconds, I close the switch, and what happens? Well, when I close the switch, if this were a regular circuit, we would immediately end up with current moving through the circuit. However, remember, the inductor, its function is, for want of a better term, to be afraid of change. Before I close the switch, the current is equal to 0 amp. And so right as I close this switch, as current would start to move, the inductor goes, no, don't want change, and it will fight against it. So at the moment I close the switch, our current remains 0. But the inductor is fighting a losing battle. It can't keep up with it completely, and part of that's actually because of some of the calculus relationships. Change has to happen. So what happens is we start from a current of 0 as charges slowly start coming out of the battery. All of the charges are spinning around here. We have very little, and then they start speeding up and getting a higher and higher current until the inductor is basically I don't want to say tired itself out, but until time approaches infinity. So let's see what we can find out here. A great question would be this. So at time equals 0, what I'd like to know is the following. When it comes to inductors, I should say, the potential difference across them, because as we've talked about with circuits, potential differences are absolutely important. Now, instead of using a delta V, they use the squiggly E, but it will act exactly like a delta V of the inductor. For inductors, we usually use a capital L. In fact, the inductance is a capital L. All right. It's actually really good for us to use the squiggly E, which is an abbreviation for electromotive force, because this actually is an electromotive force. Based off of the magnetic forces involved, it is better described that way. You may have heard me talk about my preferences in using delta V versus squiggly E in some cases rather than others. But the potential across an inductor, squiggly E, or delta V if you'd prefer, equals negative L di dt. Negative L di dt. This one's a pretty weird setup, although you can tell already that this implies that we're probably going to be doing some calculus on this. That's going to be a related video. But the IDT is basically describing how quickly the current is changing. If the current is trying to change a whole lot, then that means that with the inductor, it's going to have a large potential difference across it, and it's going to try and fight against that change. If the current is not trying to change very much at all, then we end up with a lower potential difference across it, and then eventually, as the current reaches a steady state, in other words, the current reaches a maximum and doesn't change, then di dt will go to 0, and the potential difference across the inductor will also be 0. So at the beginning, when I close this, the current is trying really hard to change, and the inductor is fighting against that and ends up with a large potential difference, which leaves very little potential difference for the resistor, which means it doesn't have a lot of current going through it. As the circuit starts getting up going, then di dt, it's not trying to change as quickly because we're starting to approach the maximum current. Things start speeding up and the potential across the inductor starts to drop, and we end up with more current, giving us more potential across the resistor. All right, at time equals 0, let's see what di dt is, basically how quickly the current is trying to change. Well, if I were to apply loop rule, again loop rule, I go across the battery, gain 6 volts, go across the resistor, lose whatever's across the resistor, go across the inductor, lose whatever's across the inductor, and we come back around to the far side. We end up at 0, so if I were to do my loop rule, I would get this. Squiggly E for the circuit minus delta V of the resistor minus, I'm going to call this squiggly E of the inductor, although it could be delta V, equals 0. These are my potential differences. This is 6 volts minus, at the very beginning, at t equals 0, I mentioned that the inductor keeps the current from, it's hard for it to change. It starts right before I close the switch, we have no current, so it starts off at 0, and when I close the switch, it stays at 0 for a nanosecond, very small amount of time, and then slowly starts moving up and speeding up. The current starts going higher and higher. But at time equals 0, at that moment, our current is still 0, and the potential drop across the resistor is the initial current times the resistance, but this is 0 because our current is 0. That means that this, the potential drop over the inductor, minus a negative L di dt equals 0. I end up with the following. Move a few things around. L in this case, I mentioned, was 5 henries. So we end up with 6 volts equals negative 5 henries times di dt. I divide both sides by negative 5, it would seem, and I'm going to end up with negative 6 over 5 volt per henry. I forget which units this comes up to, but it should actually be something along the lines of amp per second, because we'll end up with di dt. This will be equal to di dt. All right, so we've got that. Now, let's see what happens when time goes to infinity. So at the very beginning, all of our potential drop, since we have no current, all of our potential drop is over the inductor. This is in stark contrast to the capacitor. In the capacitor circuits, at time equals 0 for a discharged capacitor, as it's looking to charge up, all of the potential drop happens over the resistor, and there's none over the capacitor. For an inductor, like I said, it ends up working kind of the exact opposite. At the very beginning, there's no potential drop over the resistor, and all of the potential drop is over the inductor. But, just like with the capacitor starts to charge up, storing energy, and it starts gaining a potential difference, lowering the current and grinding the circuit to a halt. For the inductor, as time goes to infinity, it starts to store energy in the magnetic field, and because the current is no longer trying to change as it gets very close to its maximum value, or at least it's not trying to change very much, the inductor doesn't push back nearly as hard. Small changes, easier to go with than big changes. Going from 0 to a maximum current, that's a huge step. But going from 99% total to 100% total, that's a pretty tiny amount. That's not that hard to deal with. So t equals infinity. So at this point, the inductor will actually have fully charged up and it's going to stop fighting back, which means our potential difference, if I turn back to this, squiggly E minus delta VR minus squiggly E for the inductor equals 0. If the IDT, if the current reaches a steady state and is no longer changing, then the IDT is going to be 0. If the current is constant, if I take the derivative of a constant, then that would become 0. 0 times 5 henries is still 0, and we're going to find at t goes to infinity, there is no potential drop across the inductor. Which means when I fill this in, I've got 6 volts equals delta VR, which means that it's going to equal the final current times the resistance of R, which means 6 volts equals our final current times 10 ohm. We end up with the final current in this circuit being 0.6 amp. At this point, much like the capacitor, the inductor will end up fully charged. Although, unlike the capacitor, when it's fully charged, it actually just acts like a wire. When the capacitor is not charged, it acts like a wire, and when it is fully charged, it stops the circuit, or at least stops the current in its branch. For an inductor, it does the opposite. When it is not charged, it tries to stop the current, doesn't succeed, but it slows it down quite a bit, and then when it is fully charged, it just acts like a wire. So, final question on this would be, what's the total energy on the inductor at the end? We'll use another equation. The potential energy of the inductor is equal to 1/2 Li squared. So, finishing this up, my energy at the end is going to be equal to UL, potential energy on the inductor, and that's 1/2 Li squared. In this case, we're looking at the final current. Now, I say final because in my problem, we actually have it going, and we're looking at the final setting where this is completely charged. At the very beginning, when the current is 0, if we wanted to find the energy at the beginning, energy would be with the beginning current, which is 0, which would make the whole thing 0. There's no energy stored in the inductor. Finishing this up, energy final is going to be 1/2 times our inductance, which is 5 henries, times our current at the end, which is 0.6 amp quantity squared. Now again, I don't actually remember what a henry is made out of unit-wise, but this is why we have an SI system. Put SI in, amp and henry, you will get SI out. I know that my answer will be in joules. So I multiply this out. Calculator, 0.6 squared times 5 divided by 2. We end up with, if I've done this correctly, 0.9 joules are stored in the inductor in a magnetic field. Now, here's the interesting thing about inductors. Let's say that I put another branch here with another switch. Now, we could also see this with capacitors. They'll do something similar. But if I undo this switch after a really long time and close this switch, remember, inductors don't like change. So if I have 0.6 amp going through the inductor, and I open this switch but close this switch, it will try to actually keep 0.6 amp. The energy stored in this will actually go into keeping the current going, even without a battery there. This is also why this one is usually described as an electromotive force. But it'll actually keep the current going at 0.6 amp for a fraction of a second, and then the current will start to slow down as the inductor loses energy, and it will eventually come to a stop. So inductors can release that energy and actually keep a circuit going. That's the thing about inductors. They don't like to let things change, is a way of looking at this. So if you start off with no current and you close it in for the inductor, it'll go, whoa, I want to keep it at no current. But they're not 100% effective at that for a variety of reasons, luckily. And so they'll slow it down, but it'll slowly start building up steam and get going. But open this and close that, and it says, whoa, 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 now I got used to the 0.6 amp, I'm going to try and keep that. which means it will keep the 0.6 amp going, but as it loses energy, it'll start slowing back down until it runs out of energy and comes to a stop. So we can store energy in the inductor and then we can release it later. This is also why we end up with a negative in here, because it can switch depending on what you're trying to do. It can take energy and store it in the magnetic field, or if it's charged up, it can release magnetic energy into keeping the circuit going. So this is a rundown of inductors.